This discussion, I want to derive the predator-prey model, a model that we're going to work with in Chapter 2 quite a bit, but since homework number 21 from Section 1.1 uses a system, a predator-prey system, I wanted to make sure that I have shown it, or at least talked about it once. And so in this screencast, I hope to convince you of what's being described here as a description of what a predator-prey model is, and we'll see if we can write the differential equations and see if they make sense to you. So I'm just going to read through here. No species lives in isolation, and the interactions among species give some of the most interesting models to study. We conclude this section by introducing a simple predator-prey system of differential equations where one species unfortunately eats the other. The most obvious difference between this model is that from the previous things that we've done with our logistic equation is that we have two quantities that depend on time, and that's why it's called a system. Thus our model has two dependent variables that are both functions of time, and since both predator and prey begin with a P, we call the prey rabbits, and the predators are going to be our foxes. R represents our rabbit population, F represents our fox population. And here are the four assumptions. If no foxes are present, the rabbits reproduce at a rate proportional to their population, and they are not affected by overcrowding. So I'm going to start writing. I don't have much room on this screen, but I want to keep it all on one screen. So one thing I know is that the way the rabbit population changes is that it'll increase at a rate that's proportional to its population, and we've already seen that, and so this much is true. And here I'm using the letter alpha as described in this page of our text. It says let alpha be the growth rate of the rabbits. And so if there are no foxes present, the rabbit population is going to grow. The next assumption, the foxes eat the rabbits, and the rate at which the rabbits are eaten is proportional to the rate at which the foxes and rabbits interact. So when a fox eats a rabbit, we lose a rabbit. And this next term I'm going to write, which is a negative term because it corresponds to a decrease in dr dt, I'm going to use the constant of proportionality beta, and I'm going to write x times, not x, I apologize, r. r times f. And this term certainly takes a little getting used to, but what it's saying is the rabbit population will grow at a rate proportional to the size of the rabbit population, but it'll decrease at some rate proportional to the number of rabbit and fox interactions. We use multiplication to represent the interactions, so if r is large, or if r is positive and f is positive, we multiply them together, we get some positive number, and we use beta to describe the success of the interaction. So just because they see each other doesn't mean that a rabbit is eaten, but there'll be some constant proportionality that will measure how often when they see each other. So suppose r is 1,000 and f is 1,000, and that's 1,000,000, but we're not going to decrease our rabbit population by 1,000,000. Beta will be some decimal number that will correspond to the success or how often rabbits are eaten when rabbits and foxes cross paths. The next assumption says that without rabbits to eat, the fox population declines at a rate proportional to itself. So this is exactly like a growth rate, but this is a death rate, unfortunately. The size of the fox population will decrease with some proportionality constant times the size of the fox population. However, the rate at which the foxes are born is proportional to the number of rabbits eaten by the foxes, which by the second assumption is proportional to the rate at which the foxes and rabbits interact. So when a fox and rabbit interacts, there's a positive effect on the fox population. We're going to use the Greek letter delta to model the success. So now when they interact, it helps the birth rate of the foxes, and so our change in fox population will have a positive effect by this. These two equations, I'll put them in a box and put a nice color around them. These two equations constitute what we call the predator-prey model. Predator. And we'll continue to talk about these throughout the course. And in problem number 21 that I'm going to also write up, it's going to ask us to be able to interpret what these minus and plus signs mean. So one more time, a positive term here corresponds to a positive growth rate of the rabbits. The negative term here has a negative influence on the rabbit population, corresponding to how often the rabbit and foxes interact, and with beta represents the success rate of those interactions for the foxes, and how often they eat a rabbit. And again, this is a negative growth rate for the foxes without any rabbits. If R were to be 0, then this term says that our fox population decreases exponentially if there's no food to eat. But in the presence of rabbits, our fox population grows. This plus sign means that our population is growing at a rate proportional to the number of interactions between the rabbits and the foxes. That's it. Thank you.